The paradox gets its name from the star Algol, located in the constellation Perseus. Also known as Beta Persei, Algol is one of the best-known eclipsing binaries in the night sky. It appears to dim and brighten periodically, a result of one star passing in front of the other from our vantage point on Earth. This back-and-forth cosmic eclipse has intrigued stargazers for centuries, but what's going on under the hood is far more baffling. To understand the Algol paradox, we need to start with a basic concept of how stars age. Like people, stars are born, live and die, but on timescales that span millions to billions of years. A star's evolution is determined mostly by its mass. The rule of thumb in stellar evolution is, the more massive a star is, the faster it burns through its nuclear fuel. Massive stars live fast and die young, often in violent supernovae, while smaller stars can linger quietly for eons. So in any system where two stars form at the same time, the more massive one should age more quickly and evolve faster. But Algol, and systems like it, refuse to follow this script. In the Algol system, the more massive star is still happily burning hydrogen in its core, sitting pretty on the main sequence. Meanwhile, its less massive companion has already evolved into a subgiant, a star that has exhausted the hydrogen in its core and has begun the slow crawl toward its eventual demise. If both stars formed at the same time, how can the less massive one be older, more evolved, and seemingly further along in its life? That's the paradox. At first this seems like a cosmic mix-up. Maybe the stars didn't form at the same time. That idea was tempting early on, but astrophysicists quickly found it unlikely. Binary stars typically form from the same collapsing cloud of gas and dust. Their initial mass distribution and orbital relationship are shaped by that shared origin. The odds of one star being captured by another long after its formation, while possible, are vanishingly small, especially in such tightly bound systems. So if we accept that the stars form together, we're left staring at a riddle. Why is the star that should be younger already older? The solution to the Algol paradox comes from an elegant but dramatic process, mass transfer. In close binary systems, the two stars don't live in complete isolation. They're gravitationally intertwined, and under the right conditions, they can exchange matter. When one star grows large enough, either through expansion as it evolves or due to gravitational interactions, it can begin to spill its outer layers onto its companion. This stellar cannibalism changes the game entirely. Imagine the originally more massive star living its fast life, rushing toward the subgiant phase. As it swells, it fills something called its Roche lobe, an invisible boundary around each star that defines the region within which orbiting material is gravitationally bound. Once a star overflows this lobe, material begins to stream over to its companion. The less massive star starts gorging on this stellar buffet, gaining mass while its donor loses it. Over time, the mass balance tips. The formerly lighter star becomes the heavier one, but because it was originally less massive, it hasn't evolved as quickly. So now the new heavier star is still burning hydrogen like it's young, while the older star, now less massive, has already aged. This sleight of hand, where the identities and apparent ages of the stars are switched, is the key to resolving the Algol paradox. It's not that the stars defy the rules of aging, it's that they've swapped roles partway through the play. This process is complex and requires very specific orbital and mass conditions to unfold the way it does, but it has been modelled and observed in numerous systems beyond just Algol. These are now known as semi-detached binaries, where one star fills its Roche lobe and the other does not, facilitating a steady flow of mass from one to the other. But the story doesn't stop there. The Algol paradox opens up a rich avenue for studying not just binary evolution, but stellar physics more broadly. For example, the way mass is transferred, whether it forms an accretion disk, whether the transfer is conservative, i.e. all mass stays in the system, or non-conservative, some is lost into space, and how angular momentum is redistributed, can have profound effects on the system's future. In some cases, mass transfer can spin up the receiving star, making it rotate much faster than normal. This can affect magnetic activity, surface temperature, and even the internal structure of the star. Furthermore, systems like Algol are critical for testing our models of stellar interiors. Observing such systems gives us real-time evidence of processes like core fusion, convective mixing, and envelope expansion. Since binary stars can be studied with high precision, thanks to their regular eclipses and well-defined orbital dynamics, They serve as natural laboratories in the sky. Yet, despite all this progress, the Algol paradox continues to spark new questions. For one, mass transfer isn't always a neat and clean process. In some binaries, the mass loss leads to dramatic outbursts or nova-like events. In others, it seems to occur in bursts or cycles. These inconsistencies point to a deeper layer of complexity in how matter behaves under extreme gravitational and thermal conditions. And then there's the question of what happens next. As the stars continue their evolution post-transfer, new phenomena emerge. The mass gainer, now more massive and possibly rapidly spinning, could eventually evolve into an exotic object like a blue straggler, a type of star found in clusters that seems inexplicably young and massive compared to its neighbours. The donor star, meanwhile, might shrink into a compact white dwarf or become the seed of future cataclysmic activity if it continues interacting gravitationally with its partner. What makes the Algol paradox so captivating is not just its specific resolution, but the window it opens into the dynamic, evolving lives of stars. It reminds us that even something as seemingly straightforward as a star's mass and age can become a tangled mystery when gravitational bonds are in play. It also underscores a broader theme in astrophysics: context matters. A star's behaviour can't always be understood in isolation. Its history, its partners, its environment all contribute to shaping its fate. So, the next time you look up at the night sky and see Algol flicker ever so slightly, remember that you're witnessing a cosmic drama playing out in slow motion. Two stars, born together, locked in a gravitational dance, have reshaped each other's destinies through an intimate exchange of matter and energy. Their story is one of transformation, deception, and unexpected youth, a paradox that, once unravelled, tells us more about the universe than we ever expected. And while Algol was the first to pose this riddle, it certainly wasn't the last. Astronomers have since discovered many other systems exhibiting similar paradoxical traits. Each new case adds a layer of nuance, forcing us to refine our models, rethink our assumptions, and appreciate the intricate choreography of the cosmos. The Algol paradox, then, is more than just a quirk of one star system. It's a testament to the richness of astrophysical phenomena and the ever-evolving nature of scientific understanding. It's also a lesson in humility. The universe doesn't always fit neatly into our diagrams and equations. Sometimes stars break the rules, not because the rules are wrong, but because we haven't yet discovered the full story. The Algol paradox pulled back the curtain on one such story, revealing that even in the vast silence of space, interactions can be intimate, transformative, and deeply surprising. In the end, it's that sense of surprise that keeps astrophysics so endlessly fascinating. Just when we think we have the cosmos figured out, something like the Algol paradox comes along to remind us that the universe always has another twist waiting in the wings. One of the most quietly unsettling questions in the field of planetary science and astrophysics comes from what seems like a contradiction hidden in plain sight. It's called the faint young sun paradox. And while it might not sound as dramatic as a black hole or as mind-bending as a time warp, it actually touches the very foundations of how life on Earth could have begun. The paradox is deceptively simple, according to our best models of stellar evolution. The Sun, billions of years ago, should have been significantly fainter and cooler than it is today. In fact, it should have been so faint that Earth, sitting in its usual orbit, would have been a frozen ball of ice. And yet, geological evidence tells a very different story. We know there was liquid water on Earth over 3 billion years ago. Not only that, but early life was already emerging. How could this have happened if the Sun wasn't producing enough heat to keep the planet above freezing? That's the contradiction we're dealing with. And unpacking it takes us on a deep journey through astrophysics, geology, atmospheric science, and even biology. To begin, let's take a look at what stellar models tell us. Our Sun is a G-type main sequence star, and like all stars of this type, it evolves gradually over billions of years. When it first formed about 4.6 billion years ago, it began fusing hydrogen into helium in its core. But back then, the rate of fusion and the overall luminosity were lower than they are now. Models estimate that the young Sun emitted about 70% of the energy it does today. That's a big drop. It would be as if someone turned the Sun's dimmer switch down by 30%, leaving Earth with a lot less heat and light. Now, Earth's climate is incredibly sensitive to the Sun's output, A slight change in solar radiation can dramatically alter global temperatures. A 30% decrease isn't just a minor dip, it's enough to plunge the planet into a deep freeze. Think ice sheets covering oceans, land locked in permanent frost, and atmospheric changes that would make our current climate feel tropical by comparison. According to the standard energy balance equations that determine planetary temperature based on incoming solar radiation, Earth's average temperature back then should have been well below the freezing point of water. No rivers, no lakes, no oceans, at least not in their liquid form. But this is where the story takes a sharp turn. Geological records tell us something very different. Ancient rocks, known as sedimentary formations that date back to around 3.8 billion years ago, show clear evidence of liquid water. Ripple marks, rounded pebbles and mineral deposits all suggest that water was actively shaping the Earth's surface. Even more compelling isotopic signatures found in ancient minerals point to the presence of liquid water and perhaps even early microbial life. This isn't speculative stuff, it's hard evidence. So we're left with a major contradiction. The sun shouldn't have been warm enough to keep Earth from freezing, and yet Earth wasn't frozen. That's the faint young sun paradox in a nutshell. And solving it requires us to re-examine everything we think we know about the early Earth and Sun. One of the first places scientists looked for an answer was Earth's atmosphere. After all, the atmosphere acts as a blanket, trapping heat through the greenhouse effect. Today, this effect is largely driven by gases like carbon dioxide, methane, and water vapor. Could it be that the early atmosphere had much higher concentrations of greenhouse gases, enough to offset the sun's reduced output? This idea gained a lot of traction. It makes intuitive sense. If the sun was fainter, then Earth must have had a stronger greenhouse effect to compensate. Some models suggested that early Earth's atmosphere may have contained hundreds of times more CO2 than it does today. That would certainly help retain heat. Methane, a much more potent greenhouse gas than CO2, was another candidate. Produced by early microbial life and natural geological processes, methane could have significantly warmed the planet. Water vapor, too, plays a role as a feedback mechanism. It increases as temperatures rise, amplifying warming. But even this greenhouse gas hypothesis runs into problems. For one, there's a limit to how much CO2 the Earth could have had in its atmosphere. Geological processes like weathering and the formation of carbonate rocks act as long-term carbon sinks, pulling CO2 out of the air and locking it into the Earth's crust. If CO2 levels had been as high as some models require, we would expect to see much more evidence of it in the geological record. And methane, while it's potent, it's also fragile, easily broken down by ultraviolet light. Maintaining high methane levels in the early atmosphere would have required a delicate balance that's difficult to prove. Another avenue of exploration focuses on the Earth's albedo, or reflectivity. A snow-covered Earth reflects much of the sun's energy back into space. But if Earth had fewer reflective surfaces, less ice, fewer clouds, then it might have absorbed more solar radiation than current models suggest. Perhaps volcanic activity blanketed the planet with dark basaltic rocks, lowering the albedo and helping to retain heat. Or perhaps Earth's atmosphere contained particles that, rather than reflecting sunlight, absorbed it, adding to the warming. There's also the possibility that the sun itself didn't behave quite the way we think it did. Maybe our models of stellar evolution need tweaking. Could the early sun have been more active than we thought? There's some evidence that young stars can exhibit bursts of intense magnetic activity, producing solar flares and stellar winds that could influence planetary climates. If the young sun had periodic outbursts of higher luminosity, it might have warmed Earth more than our current models suggest. However, these events would likely have been short-lived, not enough to sustain warm conditions over millions of years. Some researchers have proposed even more exotic ideas. Maybe Earth's orbit was different in the past, bringing it closer to the sun, or perhaps the sun had a companion star in its youth, contributing extra radiation. These theories are far less accepted and often lack supporting evidence. But they show just how far scientists are willing to stretch their imagination to solve this paradox. Yet perhaps the most intriguing possibilities come not from a single explanation, but from the idea that multiple smaller effects work together. Maybe early Earth had a moderately enhanced greenhouse effect, a slightly lower albedo, and benefited from occasional solar flares, all combining to keep the planet just warm enough. This patchwork solution might not be as satisfying as a single elegant answer, but nature rarely plays by human rules of simplicity. Complexity might be the rule, not the exception. And in the midst of all this scientific detective work, there's the life question. Life emerged on Earth fairly early, at least 3.5 billion years ago, and possibly earlier. This means that not only was Earth warm enough for liquid water, but it was also stable enough for life to begin, evolve, and persist. Life, especially microbial life, can itself influence the climate. Early organisms could have produced greenhouse gases, changing the atmosphere and helping maintain warm conditions. This makes the faint young sun paradox not just a question of physics and chemistry, but also of biology. Perhaps life helped to solve the paradox it was born into. Over the past few decades, researchers have made progress in narrowing down the possible solutions. Improved climate models, more detailed geological surveys, and sophisticated simulations of atmospheric chemistry have all contributed to our understanding. But the paradox isn't completely solved. It continues to hover like a cloud over our theories, challenging us to refine our assumptions. The implications of the faint young sun paradox go far beyond our own planet. As we look to other worlds, Mars, Venus, exoplanets in distant systems, we rely on similar models of stellar output and planetary climate. If we can't fully explain how Earth stayed warm under a faint sun, how confident can we be in predicting the habitability of other planets? The paradox urges caution. It reminds us that planetary habitability is a delicate balance, influenced by a web of interdependent factors that we are only beginning to untangle. And there's something deeply philosophical about this paradox as well. It hints at how lucky, or perhaps how finely tuned, Earth's conditions have been. The fact that life emerged and thrived under circumstances that, on paper, shouldn't have allowed it, tells a story of resilience and adaptability. It also raises questions about how common or rare such conditions might be elsewhere in the universe. In the end, the faint young sun paradox is more than just a scientific puzzle. It's a reminder of how much we still don't know about our own home planet, and how the answers to those questions ripple outward into the cosmos. As we refine our understanding of stars, atmospheres, and climate systems, we inch closer to resolving the paradox. But perhaps its greatest value lies in the journey it inspires. A journey across disciplines, from the core of the sun to the ancient. Rocks beneath our feet, all in pursuit of one of the most profound questions of all: how did Earth become a cradle for life? So the next time someone brings up the early Earth, or the sun's life cycle, or the search for habitable planets, you might think back to this quietly powerful paradox. The young sun, too faint to warm its planets, somehow nurtured a world rich with rivers, oceans, and the stirrings of life. It's a contradiction, yes, but also a testament to the universe's ability to surprise us, to challenge our models, and to deepen our wonder with every new layer we uncover. Olbers' paradox is a timeless question that challenges our understanding of the cosmos. On the surface, it seems simple enough. If the universe is infinite and contains an endless number of stars scattered throughout the heavens, why is the night sky dark? Why don't we see a sky ablaze with light, given that theoretically every point in the sky should be covered by a star? This paradox, named after the German astronomer Heinrich Wilhelm Olbers, who formally described it in 1823, delves into fundamental issues regarding the structure of the universe. It's a paradox because, according to the assumptions of an infinite static universe, we should expect the night sky to be incredibly bright, not dark. The absence of this light raises profound questions about the nature of the universe, its structure, and its history. In this exploration, we'll dive deeply into the intricacies of Olbers' paradox, examining both the historical context and the modern understanding that helps resolve this age-old mystery. To truly appreciate the depth of Olbers' paradox, we need to first understand the assumptions behind it. The paradox is rooted in the belief that if the universe is infinite and stars are scattered uniformly throughout it, every line of sight from Earth should eventually lead to a star. And if there are infinitely many stars, then the sky should be filled with light. Therefore, instead of the blackness of space, we should expect to see the entire sky illuminated, because there would be no dark patches. Every direction would point to a star, and those stars would be shining brightly. The paradox is built on three key assumptions. The universe is infinite, there is no edge to the universe, and it extends forever in all directions. Secondly, stars are uniformly distributed. Stars are spread out evenly throughout the infinite expanse of the universe. And finally, the universe is static. The stars have existed forever, and their distribution has remained unchanged for eons. If these assumptions are true, then the night sky should not appear dark. Every point in space should be bright with starlight, because every line of sight should eventually intersect with a star. The sky, far from being black, would be as bright as the surface of a star, perhaps even brighter. Before the time of Olbers and modern astronomy, humanity had a very different conception of the universe. The ancient Greeks, for example, believed that the universe was finite but not infinite. The idea of an infinite, unchanging cosmos was largely dismissed by early thinkers, and even after the scientific revolution, the nature of the universe remained unclear. In the early 19th century, as astronomers like Olbers studied the stars more closely, it seemed intuitive to them that the universe was infinite and filled with stars in every direction. Olbers in particular questioned why the night sky was dark, given the assumption that there was an infinite number of stars. His famous paradox challenged the prevailing notions of the time, asking why, in such a universe, the sky was not ablaze with light. Heinrich Wilhelm Olbers proposed that in an infinite universe with an infinite number of stars, the night sky should be uniformly bright. However, the reality of the dark night sky contradicted this expectation. Olbers' paradox came to embody the contradiction between the observable dark night sky and the logical expectation of an infinitely bright sky. His explanation and the subsequent debates surrounding the paradox were crucial in the development of modern cosmology. To visualize this paradox, think of the universe as an infinite static space filled with stars. If the stars are evenly distributed, there would be no point in the sky that is not covered by starlight. Every point in space should be shining, because stars are always radiating light, and in an infinite universe, light should cover the entire sky. But instead, the night sky remains dark, leading to the paradox. Though Olbers' paradox initially posed a significant challenge to the understanding of the universe, a resolution began to emerge over the following centuries as our understanding of the universe itself deepened. The solutions to Olbers' paradox can be categorized into several key ideas, all of which address different aspects of our understanding of the cosmos. One of the key breakthroughs in resolving Olbers' paradox came from the discovery that the universe is expanding. This observation, first made by Edwin Hubble in the 1920 seconds, radically altered our view of the cosmos. The expansion of the universe means that galaxies and stars are moving away from one another, and the light emitted by these objects is stretched as a result. This stretching of light is called redshift. In an expanding universe, distant stars and galaxies no longer emit visible light that reaches us in the same way it once did. The light emitted by these stars is stretched to longer wavelengths, shifting it into the infrared or even radio wave regions of the electromagnetic spectrum, making it invisible to the human eye. Therefore, the further away a star or galaxy is, the less visible it becomes in the optical spectrum. As a result, the light from the most distant stars is not contributing to the illumination of the night sky in visible wavelengths. This explains why the night sky is dark despite the infinite number of stars, because light from faraway stars is redshifted beyond the visible spectrum, rendering it undetectable by our eyes. Another crucial aspect of resolving Olbers' paradox is the understanding that the universe is not eternal but has a finite age. The universe began with the Big Bang, and the light from stars has only had a limited amount of time to travel across space. This concept leads to the idea of the observable universe, which refers to the portion of the universe from which light has had enough time to reach us since the Big Bang. Because the universe is only about 13.8 billion years old, the light from stars beyond a certain distance has not had time to reach us. The observable universe is therefore finite, and there are regions of space that are simply too far away for their light to have arrived at Earth. This finite age of the universe limits the number of stars that contribute to the light we see in the night sky. Stars do not live forever. They go through a life cycle from the birth of a star to its death, which can end in various ways, such as a white dwarf, neutron star, or black hole. The finite lifespan of stars means that not all stars are shining at the same time. Many stars that might have once been visible are now dead or no longer emitting light in the visible spectrum. In an infinite static universe, there might be an infinite number of stars, but many of them would have already burned out or evolved into forms that do not emit visible light. Thus, the total number of stars that are actively shining light in the visible spectrum is not infinite, further explaining why the night sky is not completely illuminated. The universe is not empty. Between stars and galaxies, there are vast amounts of dust and gas that can absorb and scatter light. This material, known as interstellar dust, effectively dims the light from distant stars. Even if there are an infinite number of stars in the universe, much of their light would be absorbed by the dust in space, preventing it from reaching us. This interstellar dust can block and scatter light, particularly in certain wavelengths, and thus reduce the amount of visible starlight that reaches Earth. The presence of this cosmic dust explains why the sky is dark, even though there are theoretically an infinite number of stars in the universe. It is also important to consider the role of human perception in understanding Olbers' paradox. When we look up at the night sky, we are observing only a tiny fraction of the entire universe. The stars we see are part of a much larger cosmic picture, and most of the universe is far beyond our reach. The observable universe is limited by both time and space, meaning that while the universe may be infinite, our view is constrained by the finite time since the Big Bang and the immense distances between us and distant stars. This limitation of human perception means that even though there may be many stars beyond our current observational horizon, we simply cannot see them. We only observe the stars that are close enough to be within the observable universe. Olbers' paradox is a fascinating and thought-provoking question that has played a key role in shaping our understanding of the universe. The paradox challenges our assumptions about the cosmos, encouraging us to question the nature of space, time, and the structure of the universe. The dark night sky, far from being a source of confusion, is a testament to the incredible complexity of the universe and the limitations of human perception. The resolution of Olbers' paradox involves a combination of factors: the expanding universe, the finite age of the cosmos, the life cycles of stars, and the presence of dust and gas that absorbs and scatters light. Together, these factors help explain why the night sky is dark, despite the existence of an infinite number of stars. As our understanding of cosmology continues to evolve, the paradox remains a reminder of the vastness and mystery of the universe, and it continues to inspire curiosity and exploration in both professional astronomers and amateur stargazers alike. The GZK paradox, named after the Greisen-Zatsepin-Kuzmin GZK limit, represents a fascinating and unresolved mystery in the field of astrophysics. The paradox involves the observation of extreme energy cosmic rays, particles of exceptionally high energy that appear to violate the Greisen-Zatsepin-Kuzmin limit, a theoretical prediction grounded in the principles of special relativity and the physics of particle interactions. This paradox challenges our understanding of the cosmos and forces us to reconsider some of the fundamental assumptions that govern the behavior of particles traveling through the universe. In this extensive examination, we will dive deep into the history, the theoretical foundation, the observations, and the potential resolutions to the GZK paradox. Along the way, we will explore the implications of the paradox for our understanding of astrophysics, cosmology, and the nature of the universe itself. Before delving into the paradox itself, it is essential to understand the theoretical basis of the GZK limit. The GZK limit, named after the three scientists who independently predicted it, Kurt Greisen, Vadim Zatsepin, and Georgy Kuzmin, was formulated in the 1960s. Their work was based on the principles of special relativity, quantum mechanics, and the interaction of high-energy cosmic rays with the cosmic microwave background CMB radiation which permeates the universe. Cosmic rays are high-energy particles, primarily protons, that travel through space at nearly the speed of light. These particles are thought to originate from various astrophysical sources, including supernovae, active galactic nuclei, and gamma-ray bursts. When these cosmic rays travel through space, they interact with the radiation that fills the universe, particularly the cosmic microwave background radiation, which is a faint glow left over from the Big Bang. The GZK limit arises from the idea that when a high-energy cosmic ray with energy above a certain threshold collides with a photon of the CMB, it can produce a secondary particle. This interaction, known as photopion production, occurs when the energy of the cosmic ray exceeds a critical value, causing the proton to interact with the CMB photon and produce a pion, a type of subatomic particle. This process results in the loss of energy for the cosmic ray, limiting how far it can travel before its energy is significantly diminished. The threshold for this interaction occurs at energies of around 5 × 10 to the power of 19 electron volts eV, which is about 50 million times the energy of the particles accelerated in the Large Hadron Collider LHC. At this energy, a cosmic ray proton traveling through the universe would begin to lose energy due to interactions with the CMB photons. As a result, the cosmic ray would not be able to travel across vast cosmological distances without losing energy, leading to a cutoff in the observed flux of ultra-high energy cosmic rays at these extreme energies. This cutoff is what became known as the GZK limit. According to the GZK prediction, cosmic rays with energies above the GZK limit should not be observed beyond a certain distance, as they would have lost most of their energy due to these interactions with the CMB. In other words, cosmic rays with energies above the GZK threshold should be rare, and they should only come from sources relatively close to Earth. This theoretical prediction seemed reasonable based on the known physics of particle interactions and the assumption that the universe is filled with a uniform isotropic distribution of CMB photons. The first significant evidence that something might be amiss with the GZK limit came in 1991 when a cosmic ray event was detected by the Fly's Eye experiment, a large array of detectors located in Utah, USA. This event, which became known as the Oh My God particle, was a cosmic ray with an energy of approximately 3 × 10 to the power of 20 eV, far exceeding the GZK limit by a significant margin. The energy of this particle was so high that it immediately raised questions about the validity of the GZK limit. The Oh My God particle was a single proton that travelled through space, seemingly from a distant source, with enough energy to challenge the predictions made by Greisen, Zatsepin and Kuzman. The detection of this particle marked the beginning of a series of observations that would continue to challenge our understanding of cosmic ray physics and the limits on their energies. In the years following the discovery of the Oh My God particle, several other ultra-high energy cosmic rays were observed, many of which appeared to exceed the GZK limit. These observations raised significant concerns about the theoretical framework that had been built around the GZK limit. If cosmic rays with such extreme energies could indeed travel across vast distances without losing energy, it would suggest that the universe was behaving in ways that current models could not fully explain. The GZK paradox raises several profound questions for astrophysics and cosmology. If ultra-high energy cosmic rays can indeed travel long distances without being significantly attenuated by interactions with the CMB, then it suggests that the assumptions underlying the GZK limit may be incorrect. This has significant implications for our understanding of several key areas in astrophysics. One of the most immediate questions raised by the GZK paradox is the origin of ultra-high energy cosmic rays. According to the GZK limit, cosmic rays with energies above 5 × 10 to the power of 19 eV should not be able to travel over cosmological distances. This means that if such cosmic rays are being observed, they must be coming from relatively nearby sources within a few 100 million light-years of Earth. However, many of the ultra-high energy cosmic rays that have been detected seem to originate from directions that do not align with any known nearby astrophysical sources. This discrepancy suggests that either the cosmic rays are coming from sources much further away than previously thought, or there is a new unknown mechanism at play that allows cosmic rays to travel vast distances without being attenuated. The detection of these ultra-high energy cosmic rays is forcing scientists to re-evaluate their understanding of the sources of cosmic rays and to consider the possibility of new exotic astrophysical phenomena that could be responsible for these particles. The GZK paradox also raises the possibility that the observed violation of the GZK limit could be the result of new physics beyond the standard model of particle physics. The standard model, while extremely successful in explaining a wide range of phenomena, has limitations when it comes to the behavior of particles at extremely high energies. It is possible that the extreme energies of these cosmic rays are probing new regions of physics that have not yet been explored. Some theories suggest that new particles or fields, such as exotic forms of dark matter or new types of interactions, could allow cosmic rays to travel across vast distances without suffering the expected energy losses due to interactions with the CMB. These possibilities open up exciting avenues of research, as they could lead to new discoveries that fundamentally alter our understanding of the universe. The GZK paradox also challenges our understanding of the cosmic microwave background, which is thought to be a relic of the Big Bang. The CMB is a faint glow that fills the entire universe, and it plays a crucial role in the interactions between high-energy cosmic rays and the universe. If ultra-high energy cosmic rays are indeed able to travel long distances without being significantly attenuated, this could imply that the properties of the CMB are not as we currently understand them. This could suggest that the CMB is not as uniform or isotropic as previously thought, or that there are aspects of the CMB that we have not yet fully understood. In turn, this could have significant implications for our understanding of the early universe and the processes that occurred shortly after the Big Bang. Given the serious implications of the GZK paradox, scientists have been actively working to find explanations that can reconcile the observations of ultra-high energy cosmic rays with the theoretical predictions of the GZK limit. Several potential resolutions have been proposed. One possibility is that the sources of ultra-high energy cosmic rays are much more energetic than previously thought. If cosmic rays can be produced by extremely powerful astrophysical events, such as the mergers of black holes or the acceleration of particles near supermassive black holes, it may be possible for these cosmic rays to travel vast distances without being attenuated. These sources could be far more efficient at accelerating particles than previously realized, and their extreme energy could allow the cosmic rays to overcome the GZK limit. As mentioned earlier, the GZK paradox may be pointing toward new physics that extends beyond the standard model. For example, some theories suggest that exotic particles, such as dark matter candidates, could interact with cosmic rays in ways that bypass the expected energy losses from interactions with the CMB. These new particles could allow cosmic rays to travel longer distances without losing energy, explaining the observed violations of the GZK limit. Another possibility is that our understanding of the cosmic microwave background and its interactions with high-energy cosmic rays is incomplete. It may be that the CMB is not as uniform or isotropic as previously thought, or that there are unknown factors that influence how cosmic rays interact with the CMB. A deeper understanding of the CMB and its properties could help explain why ultra-high energy cosmic rays are able to travel across vast distances without losing energy. The GZK paradox represents one of the most intriguing mysteries in modern astrophysics. The observation of ultra-high energy cosmic rays that appear to violate the GZK limit challenges our understanding of the universe, particle physics, and the nature of the cosmos itself. While several potential resolutions have been proposed, the true answer remains elusive. Whether the solution lies in new astrophysical phenomena, new physics beyond the standard model, or a re-examination of the properties of the cosmic microwave background, the GZK paradox continues to drive scientific inquiry and inspire further exploration of the universe's most extreme phenomena. The paradox of youth in the galactic center is a striking conundrum in astrophysics that has puzzled astronomers and astrophysicists for decades. The paradox revolves around the unexpected abundance of young stars near the supermassive black hole at the center of our galaxy, Sagittarius A, and the fact that this observation does not align with theoretical predictions regarding star formation in such an environment. Understanding this paradox requires a deep dive into the astrophysical processes governing the galactic center, the life cycle of stars, and the intricate relationship between black holes and their surrounding stellar populations. In this extensive discussion, we will explore the nature of the galactic center, the formation and evolution of stars near supermassive black holes, the theoretical predictions that suggest such a young stellar population should not exist, and the various hypotheses that attempt to resolve this paradox. Along the way, we will examine the implications of these findings for our understanding of galactic dynamics, star formation, and black hole physics. At the heart of our Milky Way galaxy lies a supermassive black hole known as Sagittarius A, with a mass of approximately 4 million times that of the Sun. Sagittarius A is located around 26,000 light-years from Earth, in the constellation of Sagittarius, and it is surrounded by a dense, dynamic environment of gas, dust and stars. This region, known as the galactic center, is one of the most active and intriguing parts of our galaxy, and it has been the subject of intense study over the years. The galactic center is a complex and chaotic region with a variety of astrophysical processes taking place. It is home to a wide range of objects, including massive stars, molecular clouds and accretion disks, as well as a variety of compact objects such as neutron stars, white dwarfs and black holes. The environment around Sagittarius A is hostile to star formation due to intense radiation and tidal forces, and yet it is here that an overabundance of young stars has been observed. In order to understand the paradox of youth, we must first examine the theoretical expectations for star formation in the vicinity of a supermassive black hole like Sagittarius A. Theoretically, star formation in this region should be inhibited for several reasons. The immense gravitational pull of Sagittarius A exerts tidal forces on the surrounding gas and stars. These tidal forces are so strong that they can disrupt the formation of new stars. In the inner regions of the galactic center, where the gravitational influence of the black hole is strongest, it is thought that the conditions are too extreme for stars to form in the traditional way. Instead, the gas and dust in this region would be torn apart before it could coalesce into new stars. The galactic center is an environment of intense radiation, primarily emitted by the supermassive black hole and the nearby stars. This radiation can prevent the collapse of gas clouds, which are the typical precursors to star formation. The energy from the radiation can heat the gas, preventing it from cooling and condensing into dense regions where stars can form. This taint radiation pressure is another factor that inhibits star formation close to Sagittarius A. The region around Sagittarius A is densely packed with stars, and the close proximity of these stars can lead to frequent gravitational interactions. These interactions can disrupt the formation of new stars by scattering the gas and dust, preventing it from settling into the dense clusters that are necessary for star formation. This process, known as dynamical friction, can cause the gas to be ejected from the region or be pulled into the black hole, further hindering star formation. Given these factors, theoretical models predict that star formation should be extremely rare or even impossible in the immediate vicinity of the supermassive black hole. However, the observations tell a very different story. Despite the theoretical predictions, observations of the galactic center have revealed an overabundance of young stars in the region closest to Sagittarius A. These young stars, some only a few million years old, are found in close proximity to the black hole within the so-called central parsec, a region roughly 1 to 2 parsecs in radius, approximately 3,000 to 6,500 light-years. These stars are typically much younger than those in other parts of the galaxy, where star formation has slowed down or ceased entirely. One of the most striking features of these young stars is their presence in the dense stellar environment near the black hole, where it was once thought that star formation should be impossible. The discovery of these stars challenges our understanding of how stars can form and evolve in such a hostile environment. The population of young stars near Sagittarius A is diverse, including both massive stars and smaller stars similar to the Sun. These stars are typically located in two distinct groups: the Dunnes stars, which are orbiting close to the black hole, and a more diffuse population of stars that are scattered throughout the region. The S stars in particular have orbits that suggest they formed relatively recently, within the last few million years. In addition to the S stars, astronomers have also discovered a number of massive young stars that appear to be in the process of formation. These stars are located in dense clusters within the central parsec, where they are being heavily influenced by the radiation and tidal forces from Sagittarius A. The fact that these stars are still forming in such an extreme environment is puzzling, as it seems to contradict the theoretical models that predict a lack of star formation in this region. The paradox of youth, with its seemingly contradictory observations and theoretical predictions, has led to a number of hypotheses aimed at resolving the discrepancy. These hypotheses seek to explain how young stars can exist so close to the supermassive black hole in the galactic center, despite the extreme conditions that should prevent their formation. One possible explanation is that the traditional mechanisms of star formation do not apply in the galactic center. Instead of the usual process of gas clouds collapsing under their own gravity, it is possible that stars in this region are formed through alternative mechanisms, such as the accretion of gas from the surrounding environment or the merger of smaller stellar objects. These processes could allow stars to form in conditions that would normally be considered too extreme for traditional star formation. For example, it has been suggested that the high-density gas and dust near Sagittarius A could be heated and compressed by the intense radiation from the black hole, causing it to collapse into stars. This process, known as photoevaporation, could lead to the formation of stars in a way that bypasses the usual constraints imposed by radiation pressure. Additionally, the presence of massive gas clouds in the galactic center, which may be interacting with the supermassive black hole, could provide the necessary material for star formation. The gas clouds may be stripped of their outer layers by the radiation from the black hole, but the remaining material could still collapse to form stars. Another possible explanation involves the relativistic effects of the supermassive black hole on the orbits of nearby stars. The extreme gravity of the black hole could be causing the orbits of nearby stars to evolve in such a way that they are able to form in close proximity to the black hole, even in the face of radiation pressure and tidal forces. This could explain why we see young stars near Sagittarius A, despite the theoretically prohibitive conditions. In particular, it has been suggested that the orbits of stars in the galactic center could be influenced by the black hole's gravitational pull, in such a way that they are able to retain their youthful characteristics, even as they pass through regions of intense radiation and gravitational stress. These stars may be forming in a stable equilibrium that allows them to survive in an environment that would normally be hostile to star formation. A more radical possibility is that the galactic center contains exotic physical processes that we do not yet fully understand. These processes could allow for the formation of stars in ways that are fundamentally different from what we observe in other regions of the galaxy. For example, the strong magnetic fields and intense radiation in the galactic center could be interacting in ways that facilitate star formation, even in the presence of the black hole's immense gravitational pull. In addition to these physical processes, the supermassive black hole itself may play a direct role in the formation of stars. The accretion disk surrounding Sagittarius A could be acting as a source of energy and material for star formation, supplying the necessary gas and dust for the creation of new stars. The dynamics of the accretion disk could lead to the formation of dense pockets of gas that collapse into stars, despite the otherwise inhospitable environment. The paradox of youth has important implications for our understanding of the galactic center and the processes that govern star formation in extreme environments. It challenges the idea that star formation is always inhibited near supermassive black holes and suggests that there may be unknown or poorly understood processes at play in these regions. Resolving this paradox could lead to new insights into the behavior of black holes, the nature of stellar evolution, and the physical conditions that govern the formation of stars in different parts of the universe. In addition, the paradox has implications for our understanding of galactic dynamics. The existence of young stars near the black hole could provide valuable clues about the past history of the galactic center, shedding light on the processes that shape the structure of the Milky Way. It may also offer insights into the formation of supermassive black holes themselves, as the interactions between black holes and stars in the galactic center are thought to play a key role in the evolution of galaxies. The paradox of youth in the galactic center is a fascinating and unresolved mystery in astrophysics. The abundance of young stars near Sagittarius A, despite the extreme conditions that should inhibit star formation, challenges our understanding of stellar evolution and the behavior of supermassive black holes. While several hypotheses have been proposed to explain this paradox, much work remains to be done in order to fully understand the processes at play. The resolution of this paradox could have profound implications for our understanding of the universe, shedding light on the intricate relationship between black holes, stars, and the dynamics of galactic centers.